This video is going to go through the 2.2a warm-up and the 2.2b notes. Remember, if you have questions from the homework, that you can save them for tomorrow, and I'll be able to go over any of those questions. So the first one says, does the given information represent a function? Remember, when we're using points to check that the x cannot repeat with a different y. And when we're looking at an equation, the y can't be raised to an even power, or the y cannot be an absolute value, which would result in those sideways graphs, which is where the vertical line test comes into play. So if I look at number 1, I want to compare all the x values. I've got a 0, a 2, and a 3. None of them repeat. So this does represent a function. Number 2, I'm looking for, again, y raised to an even power, y an absolute value, and that does happen this time. So this is not a function. The next set of instructions says to evaluate the function f of x equals x squared if x is less than 0, or x squared plus 2 if x is greater than or equal to 0. So this is our piecewise function. We look at the value inside the parentheses, which is what we normally plug in for x, and figure out which range it falls in. Is it less than 0, or is it greater than or equal to 0? Since 2 is greater than or equal to 0, we're going to use the second expression. So we're going to plug this into x squared plus 2, and I get 2 squared plus 2, 4 plus 2, which is 6. And number 4 says find the value of the function so that f of x equals 0. And I've got f of x equals x to the third minus 2x squared minus 2x plus 4 over 5. So I want to find the value that makes the f of x, which is this part here, 0. So I'm going to set that entire function equal to 0. 0 would equal x to the third minus 2x squared minus 2x plus 4 over 5. I want to get rid of that denominator first, so I'm going to multiply both sides by 5. 5 times 0 is 0. X to the third minus 2x minus 2x squared, minus 2x plus 4. The 5's cancel. So now, when I see that I have 4 terms, I know I'm going to have to factor by grouping. Group together the first 2 and the last 2. From the first set of parentheses, I can take out an x squared, and I get x minus 2. Second set of parentheses, I need to change those signs, so I'm going to take a negative 2, and I get x minus 2. So then I get x minus 2 and x squared minus 2. I'm going to set each of these equal to 0. So the first one, x would equal 2, and the second one, x squared, would equal 2. X would equal plus and minus the square root of 2. So remember to do that plus or minus when you're square rooting both sides to solve. So there are 3 values that makes f of x 0, negative square root 2, square root 2, and 2. And that completes the warm-up for part 1 of 2.2. All right, so chapter 2, section 2b is still functions, but we're focusing on the domain of the functions. So the domain of the function is basically the values that can be plugged in for x, so the x values of it. If you're looking at a graph, then the domain is going to be the points from left to right, because again, that makes sense. That's the x values from left to right. So in a moment, you'll see you could be given coordinate points, and if I want to find the domain, I just grab all the x values. If I was looking at a graph, I'd go from left to right, which we'll do in the next section. And then there's rules for domain in equations that we're going to talk about next. And those are these. So the domain of a function from an equation. Now the default or original is all real numbers. So if I just had y equals 2x minus 7, my domain is all real numbers. There are 3 exceptions to this rule. The first is if there's a variable in the denominator. So if I had something like 1 over x, then I would find my domain by setting the denominator not equal to 0. So I would say that x cannot equal 0, and that would be my domain restriction. If it was 1 over x plus 1, now I'd say that cannot equal 0, so x cannot equal -1. And that's my domain restriction. The second exception to all real numbers is if there's a variable underneath a square root. So if that's the case, if I have a variable underneath the square root, then I would say whatever's underneath the square root has to be greater than or equal to 0. And that happens because we can't square root a negative number. Just like the first one happens because I can't divide by 0. It would be undefined. So if there's a variable under a square root, I set whatever's underneath that root greater than or equal to 0 to get my domain. So this is an inequality. This example would be x is greater than or equal to 0. And the last example is if there's a variable underneath the square root in the denominator. So the combination of the other two. And that now means it can't be less than 0 because it's a square root, and it can't be equal to 0 because it's in the denominator. So for that case, I take my expression that's underneath the square root and I set it greater than 0. Okay, so let's work through some examples. The directions here will always say the same thing: find the domain of the function. So if I look at number 1, here's my example that has just points. So I look at all my x values, 3, 4, 5, and 8, and just list them. 3, 4, 5, and 8. For number 2, I get f of x equals -2x plus 1. So now we've started the equations. Remember, for the equations, we're looking for a variable in the denominator. We're looking for a variable underneath a root, or the combination, the variable underneath the root in the denominator. None of these 3 cases are happening here, so this is actually an all real number scenario. There's no restriction. If you look at 3, you get f of x equals -2/3 x minus 1. Again, there's a fraction here, but the variable is not in the denominator, so this is also all real numbers. Looking at number 4, f of x equals x squared plus 1. Again, no variable in the denominator, no square root, so all real numbers again. And the same is also true for number 5. An exponent has no bearing unless it was a negative exponent to bump it to the bottom, which this is not the case. This would be all real numbers. Now looking at number 6, this is the first time we have a variable in the denominator. So I would set my denominator not equal to 0. If I needed to solve, I would, but x is already isolated. So the way this would be written, and you'll see it on WebAssign, is all real numbers except x equals 0. Now, if you were just writing this down as an answer, you could also have written x cannot equal 0 like that. But your WebAssign will say it written like that. It actually says all real numbers x except x equals 0. All right, continuing with our examples. Looking at number 7, this also has a fraction. So the variable in the top is totally fine. I don't have to worry about it because I can have a 0 in the top. It's the variable in the denominator that's the problem. So I would say x minus 5 cannot equal 0, and then add 5 to both sides, and x cannot equal 5. So all real numbers except x equals 5. So if you're trying to if you're just writing out your work answers, feel free. This little fancy R represents all real numbers. So you can write that except 5, or you can write x cannot equal 5 in your work, and then just make sure you make the selection that makes sense when you go to WebAssign. All right, number 8, again, variable in the denominator. So I would say my denominator cannot equal 0, subtract the 1, 2x cannot equal -1, and divide by 2, x cannot equal -1/2. So all real numbers except x equals -1/2. Moving to number 9, a variable in the denominator. So I set my denominator not equal to 0. Now this time, this can be factored. So you can look at this two ways. One is factor it, difference of two squares. The other is even root property. So if I factor it, I would say neither of these can equal 0. So x cannot equal -1 and x cannot equal +1. Or if I use the even root property and I square root both sides, I'd get x squared cannot equal, and I put that plus and minus, plus or minus 1. So same answer, two methods, but they're both right. So now this is all real numbers except x equals -1 or x equals +1. If you're just writing it in your notes, you can write x cannot equal positive or -1. So this would be the answer selection from WebAssign, but work in your homework can just be this. Okay, moving on to number 10. So I have a variable in the denominator. I would say that this cannot equal 0. Now this time, this is a plus, so it can't be factored. If I did x squared cannot equal -4, and then I square root both sides, I'm looking for real numbers here. So this negative means that there's no value that I can plug in for x to get -4. And since that's the case, this is all real numbers. So again, we can't solve that because we're not using i's. We're talking about real numbers. In that case, my answer would be all real numbers. Number 11 is our first one with a square root. So we did this with an example, but remember, if there's a square root, that whatever's underneath it has to be greater than or equal to 0. There's nothing to solve for there, so I would just say x has to be greater than or equal to 0. In words, this would be all real numbers greater than or equal to x equals 0. Number 12 says f of x equals the square root of x minus 3. So everything underneath the square root gets set greater than or equal to 0. X minus 3 would be greater than or equal to 0. Add the 3. And x would be greater than or equal to +3. So all real numbers greater than or equal to x equals 3. The wording on WebAssign there is actually all real numbers, x such that x is greater than or equal to 3. All right, continuing our examples, number 13 also has a square root. So I want to set that greater than or equal to 0. 2x would be greater than or equal to 1. Divide both sides by 2. X is greater than or equal to 1/2. So all real numbers such that x is greater than or equal to 1/2. F of x equals the square root of x minus x. This has to be greater than or equal to 0. So if you want to move the x over, this would be 4 is greater than or equal to x. Remember, it should make sense to flip it. but you want the small part to still be pointed toward the x. So now we're saying all the real numbers less than or equal to 4. Or all the real numbers where x is less than or equal to 4, like that. Okay, so 15 and 16 are a little bit more challenging because that square root is now in the denominator. So because we've moved it to the denominator, it's no longer a greater than or equal to 0. It's just greater than 0. Because if I let it be equal to 0, then my denominator makes this undefined. So it can't equal 0, it's got to be greater than. So here it's just x has to be greater than 0. So all real numbers such that x is greater than 0. For 16, I would set 2x minus 1 greater than 0. So 2x minus 1 is greater than 0. Add the 1. 2x is greater than 1. Divide by 2. X is greater than 1/2. So all real numbers such that x is greater than 1/2. Last set of examples here, and again they get a little bit more complicated because you have a square root in the numerator and the denominator. So we basically have two restrictions going on here. So let's start with 17. I'm going to look at the numerator and say the numerator has to be greater than or equal to 0 because there's a square root there, and the denominator has to be greater than 0 because that square root's now in my denominator. So I'm going to solve the first one. X minus 1 greater than or equal to 0 would give me x has to be greater than or equal to 1. Now the second one is x plus 2 has to be greater than 0. So x has to be greater than negative 2. So if you could picture these on your number line, the first one is that it's greater than or equal to 1. So it'd be a bracket pointing to the right here, or a solid dot pointing to the right there. And the second is that it has to be greater than negative 2. So greater than, not with an equal to, gets a parentheses, shaded to the right. Now both of these have to be true in order for a variable to work, or a function, a value to work in that variable. So I only take where the overlap happens, which starts at positive 1 and goes to positive infinity, or this part of my inequality. So this is all real numbers such that x is greater than or equal to 1. So we have to take the more restricted inequality here. It would start where they overlap, which happens at 1 and greater than 1. Greater than or equal to 1. Okay, let's try another one of those. So 18, again, both in the numerator and the denominator. The numerator gets a greater than or equal to 0. The denominator gets a greater than 0. So 2x minus 1 greater than or equal to 0. 2x greater than or equal to 1. X greater than or equal to 1/2. Denominator, x plus 3 greater than 0. X greater than negative 3. Looking at my number line, the first one greater than or equal to 1/2. The second one greater than negative 3. Again, we only can use where they overlap, which is the greater than or equal to 1/2. So all real numbers where x is greater than or equal to 1/2. And the last one, usually the most fun. That was sarcasm. Looking at the denominator, I'm going to set that greater than 0. And my numerator greater than or equal to 0. So the numerator, x minus 1, greater than or equal to 0. X is greater than or equal to 1. The denominator, we've got a polynomial that's raised to a second power, or quadratic, with an inequality. So remember with these, we're going to set it equal to 0. This can be factored, or even root property. -9, +9. And then we have to test points here. So if I had -9, +9, I'm going to test a point. So let's pick the easy one, the 0 in between. Plug 0 in, and I get -81 is greater than 0. That's not the case. So it's probably outside. -10. So -10 would be 100 minus 81. That is greater than or equal to 0. And +10 would be 100 minus 81, which also works. So for that part, just the denominator, I would get that x has to be less than -9 or greater than +9. Now, because all of those have to work, I'm going to plot all 3 parts on my graph. The greater than greater than 1 is a bracket pointing to the right. The less than -9 is a parentheses pointing left. And the parentheses on the 9 pointing right. So now we're saying that this has to be true. This part, okay, has to be true, which means I have to use the orange. But then with the bottom, we're saying it's either this or that. So because the -9 pointing to the left does not overlap with the orange at all, we overrule that part. And then on the right, we take where they overlap. So that actually starts at 9 and points to positive infinity. So it's a this and this or this. Because this did not overlap with this one, you cannot keep it. This does overlap partially with that one, which means that my answer here is it has to be greater than 9 and not equal to, because there's no or equal to here. So this would be all real numbers such that x is greater than 9. So if I get 2 parts and one of those parts is an or, then it has to be true for the top part in this case, and then it can be part, either of the or statements have to overlap. All right, that wraps up the notes for 2.2b, well, and 2.2 in general. You make sure that you turn in those notes. Those completed notes, okay? And then use the rest of the time to work on the 2.2 part 2 homework. You guys have a fantastic day, and I will see you tomorrow.